I had babies. Like, oh, like, not, so like, this right here, and all like these things. I want to buy right, yeah. Yeah, I actually sizing of the bag. Yeah, that was my first one. Yeah, I don't.
Right, this is page 1 from your new packet. Now this we're starting the next section. Obviously, this is not going to be on your quiz tomorrow. Your quiz is just over the worksheets that we've been working on. So tomorrow I will have a morning help session at 7:15, going over worksheet 3, and then we can also maybe do 1 or 2 problems at the end of class today in preparation for tomorrow. So we're going to kind of extend the idea that we've learned, kind of combine a couple of things together. We know that we've been using rectangles to approximate area under a curve, and also we did the limit definition or area limit definition of area. But we have a much more efficient way now of finding area under a curve, and we're going to be using power rule to help us get there, or the antiderivative to get there. So we're merging a couple of things together from what we've learned in the past week or so. So this is a general formula where we now have bounds that we can work with. Okay, so before there weren't any bounds, and we would just say, okay, the antiderivative, whatever that rule is, then we'll do a plus c, because there's a family of functions that all share that same derivative. But now we want to think of it as this function, this curve. We're going to find a formula that can help us find the area under this particular curve. So what we do is this lowercase f is going to turn to uppercase f, and that's just a general process of whatever the antiderivative rule is to produce that antiderivative function. And then we're just going to plug in the upper and the lower bound, f of b minus f of a. The result of this is going to essentially produce the area under this original curve. So we're creating a formula that, or using a formula that will give us information about the original function's a shaded region. There's different variations of this, and I'll put another variation of it up here. We can also do this, the integral from a to b of f prime of x dx. And f prime, its antiderivative is simply f, and then we can plug in the upper bound minus the lower bound. So if you ever see lowercase f to uppercase f, that just indicates the process of finding the antiderivative. But then, I'm sorry, I don't know why I put p there. Minus, oh, it was f, I just listed p. But this is a more specific example where if I have a specific f prime, then f prime is going to rise up to f. And then another variation is if I'm starting with f double prime, then the antiderivative is just f prime, and then I can plug in my upper bound minus lower bound. So all these different variations, they all are basically, this is first theorem of calculus, first fundamental theorem of calculus. That process of finding the antiderivative and then working the bounds into the answer. So when we do a general derivative, this is from first semester, we know a derivative is a slope finding function, right? If I find f prime of some function, then that f prime can be used to find the slope of the original function I started with. And then a specific derivative is the actual slope at that point, right? So first semester, we were able to create a slope formula that can give us information about any point on the curve. And then we can plug in a specific number to get a slope at that particular point. And this semester, the indefinite integral is an area finding function. So if I did the antiderivative of 2x dx, power rule becomes x squared plus c. X squared plus c is basically, can be thought of as not only the antiderivative, but it's also potentially describing the area information under the original graph. And then if I want to find the actual area for a specific region, I can involve bounds, find the antiderivative, and then plug in the upper and lower bounds, which are the left and right endpoint, to give me the number that's associated with the area of that region. If a function is continuous on a closed interval, okay, if there are no breaks in the graph, then the function is able to be integrated on that interval. Okay, so let's try example 1 here. Now, whenever you see bounds involved in your antiderivative, you want to keep in mind one important thing is that this is the last step in the problem. Okay. We are never going to be plugging the bounds into the function that we see. And I know that maybe why students want to do that is because, you know, we typically read from left to right. So if we read from left to right, we're thinking, okay, the 1 and 4 is the first number I see, so maybe that's the first thing that I do. But it's actually the last thing that we do. Okay, so we're going to imagine like as if the bounds aren't there, and we're just going to take the antiderivative of 3x squared plus 4x minus 1 and just treat it like as if the bounds aren't there. So I'm going to start off doing this problem. So again, whenever you see bounds, ignore it. That's the last thing that you do. We're going to first take care of that indefinite integral. So indefinite integral is the process without the bounds. So it looks like we can just go through power rule. Every term can be, we can have the power rule applied there. So we add 1 to the exponent. This becomes what? 3x squared becomes what? I'll clean this up later. 4x becomes 4x squared over 2. The 1 becomes x. Yeah. Now we have bounds involved here from for this problem, so we're not going to put a plus c. The plus c would indicate that there's a family of functions that all share the same derivative, but now we're pinpointing down to a specific number. We're trying to get an area of a region, so we're not going to put a plus c, and rather to indicate that we're ready to involve the 1 and 4, we're going to put a half bracket there. A half bracket just indicates I have my antiderivative. I'm ready to use my upper and lower bounds to be involved in my answer. So what we did just now, we're basically creating that uppercase F. Okay, we found the antiderivative, whatever that process was. In this case, it was power rule. And now we can work in the B and A. We're going to plug in the upper bound minus lower bound. So this process is going to be indicated by this half bracket here. So the top number always gets inserted in first. And I'm going to do a little bit of cleanup here. I don't have to include that 3. We know 3's cancel out. And we know this is just going to be a 2 here. Okay. So the 4 gets plugged in first. The 4 replaces every x in the antiderivative. So it becomes 4 cubed plus 2 times 4 squared minus 4. And that's basically what that f of b is doing. We're applying that f of b step there. Minus, big parentheses, And then do the same thing with the 1. Plug in the 1 in for all the x's. 1 cubed plus 2 times 1 squared minus 1. And then whatever number we get in return, that numeric value is going to be an area-related answer. I'm going to keep saying area-related because if the region is below the x-axis, then we may get a negative number. But for large part here, we're just going to call this area, but technically it's displacement. But if everything is above the x-axis, then this would give us the area of that exact area of that region below the curve and between 1 and 4. So we're essentially applying this formula, right? We took the antiderivative, we made that original function rise up to the antiderivative, and then we plug in the upper and lower bound. So we're basically using this formula to tell us about the area of this original curve, or the area under this original curve. And then for definite integrals, we don't need to worry about the constant of integration plus c. It will always wash out. So if you see bounds involved, after you find the antiderivative, you're not going to put a plus c. If you don't see any bounds, then you can do a plus c once you find your antiderivative. Okay, let's look at example 2. Evaluate the definite integral from -2 to 1 of 2x dx. Remember, the bounds are always the last thing that you do. You're going to ignore the bounds and take care of the antiderivative. Like I said, if you don't see the bounds, and then save the bounds for the very last step. Okay, so this is a good candidate for power rule. Right now, we only know power rule and trig integrals. This is power rule here. The term is ready for us to be applied. So we're going to take the antiderivative. 2x becomes and the 2's can cancel out, right? Now that we have the antiderivative, we don't put a plus c because we're getting ourselves ready for the bounds. Half bracket to indicate that we want to plug in the bounds. Upper bound first. Followed by lower bound. What does this give us here? -3, yeah. 1 minus 4. The -2 squared will resolve first. This will become a positive 4. And 1 minus 4 becomes -3. And, we don't associate negatives with area. And the reason why we're getting that is because the graph looks something like this. And we're looking, basically what this is doing is this is finding that region between -2 and 1. So it's telling us information about that shaded region. But here, these are accumulations of negative y values because these are all below the x-axis. So this ends up being a -4 plus 1, which is why we're getting a -3. So if you ever see a negative for antiderivative for a definite integral, that should indicate to you that there is a region that is, there's an area region that is more below the x-axis than there is above the x-axis. So if we have portions below the x-axis, that indicates that negative value. So we typically call this a displacement that's why we can have that being a negative value. Later on in future units, we're going to have something, we're going to adapt this integral so that we can always get a positive number, so we can call it area. But right now, we may get a negative answer, which is area related, but it's not quite area. It's more displacement. All right, next page. Here, we have some integral properties that's useful for us to apply. The first property is that if I'm trying to find an area of a region and my bounds don't move, meaning that if I start at 1 and I end at 1, that means if I haven't moved at all, there's no width. If there's no width, there's no area. Well, there's an area. That area is always going to be 0, though. So if ever my bounds are the same, my definite integral is always going to be 0 because there's no area for me to find. Second is sometimes we may want to adjust the bounds for sometimes certain problems. It's easier sometimes to, if the integral is presented backwards, like from like 5 to -4, sometimes we prefer to read the graph from left to right, so we're not having to do everything backwards in our minds. So sometimes a property that helps us for certain problems is just rearranging the bounds. But if you ever want to rearrange the bounds, you want to make an adjustment. So that adjustment is having to pull a negative out in front. So for instance, if I'm trying to do something, let's say from 5 to -4 of f of x dx, and it's kind of going backwards here, my lower bound is higher than my upper bound, I can do this. I can make the lower bound be the smaller number, but if I'm making a change to my bounds, I also need to pull a negative out in front. I want something that is still equivalent to what I started with, but this just makes it easier for us to interpret a problem. So yeah, whenever you want to flip the bounds and you don't, and you're still trying to maintain the same equivalent expression as what you started with, you got to make sure you include a negative. The third property, sorry, there's a stray mark there. I don't mean for there to be a negative. It looks like there's a negative in front of that f of x. This is saying that sometimes it's helpful to break up a larger region into smaller regions. So let's say C is between A and B. And let's say the graph looks something like this. In some problems, it's useful to break a larger problem into smaller parts. So let's say I have the integral from A to B of f of x dx, and I want to break it up into smaller, easier parts to work with. And let's say C is between A and B, I can then break it up into the definite integral from A to C plus the definite integral from C to B, and then handle them in smaller chunks. All right, so example 3, we have some properties that we're going to use, and we can also apply some of these integral properties to help us with our answer. So we have a region from 0 to 3 that's equal to 4. We have a region from 3 to 6 that's below the x-axis, or sums up to be below the x-axis, which is -1. And now we want to find the definite integral, the accumulated region from 0 to 6. And here we have a portion, half of the portion on this side, half the portion between 3 and 6. So we know that the integral from 0 to 6, we can say, okay, 0 to 3, will give me half that region, and 3 to 6 will give me the other half. And then if I have these individual parts in front of me, I can just make a substitution. We know this is equal to 4. We know that's equal to -1. So then 4 minus 1 is equal to 3. We are asked about the definite integral from 6 to 3, but we have the integral from 3 to 6. So what can I do with this to make it look more like the rule with the property that I have in front of me? Flip it and yeah, pull a negative out, right? If I'm changing the problem by changing the bounds, I gotta undo that change with a negative in front. So now that I've created something equivalent so that I can match my property better, I can make a substitution, right? I know that this piece is equal to what? -1. And then if I have a negative and a -1 together, I can cancel that out to be just +1. What do you notice about part C here? If bounds are the same, my definite integral is always going to be what? 0. Doesn't matter what my function is. Part D, it's a little tricky because you may be looking at that 3 feeling like, oh, that 3 is just like a number by itself. That 3 is under the umbrella of the definite integral, so that 3 is getting impacted by the integral. So let me split this up. This portion is referring to f of x. We can rely on our property that's given to us at the top of the page to make substitutions. But this is its own standalone problem. We're actually going to be using power rule for this problem. What's the antiderivative of 3? 3x. Okay, so this is going to turn into 3x, and then we're going to evaluate the bounds separately from 3 to 6. Okay. This feels like a 3 that just, oh, I'm just going to add 3 to whatever my result is, but that 3 is under the integral umbrella. We have to go through a separate process there. Okay, so this upper bound first. So the second half of the problem will give me 9. The first half of the problem, I'm going to pull the -5 out in front just so I can see my property a little bit better. And I have a clean substitution for this piece, right? I can replace this piece with what? Three to 6 equals -1. Yep. And so -5 times -1 is 5. And so we add these numbers together. 5 plus 9 is 14. Any questions? AP exam, they love to use this first theorem to see if students can interpret and solve in different scenarios. So here's an example. If the definite integral from 3 to 8 of f prime is equal to 10 and f of 8 equals 6, find f of 3. So this FFTC, this is just a abbreviation for first fundamental theorem of calculus, can be used as an equation solving tool to find the value of the antiderivative at a specific point. So if we know that the definite integral is coming from this formula here, what if I were to replace 3 and 8 in for A and B? So I know that 3 and 8 are involved here. So if I say, we know that if I'm just given the integral from 3 to 8 of f prime, even without knowing that it's equal to 10, I know I can break this down into the function parts, right? We know f prime is going to rise up to f, and then we can plug in our upper and lower bounds. So we know that's equivalent to f8 minus f of 3. And if I can have this in front of me, I can make some substitutions, right? I know that I can replace this with what? What do we know about, what do they tell us that's this equal to? 10. We know f of 8 is equal to 6. And the only thing that we're looking for is that f of 3. So now this becomes an equation that we can solve for f of 3, right? Example 5, the area for each region is given. Find the definite integral from a to b of f of x dx. So the area is given, but we're talking about definite integral here. So anything above the x-axis will remain a positive, but anything below needs to be adjusted to be what? Below the x-axis. The area is 2, but the definite integral is what? -2. Right, so if I were to find the definite integral from a to b, it'll be 10 minus 2 plus 3. Any questions? Okay, so that's basically what I want to cover today. Let's go back and do some review from our for our quiz. Again, I want to talk about what you're expected to know for your quiz. I will give you the summation formulas. I will give you area using limit definition. I'll give you the width formula, but you're going to be expected to memorize the trapezoid area. You'll be expected to memorize power rule. and then also your trig integrals. But we talked about how your trig integrals, don't feel like you're trying to memorize these rules, just use the rules that, write out your derivative rules for first semester and just know that you're starting on the right side and moving to the left. So the antiderivative of cosine will be sine, the antiderivative of secant squared, tangent, the antiderivative of secant, tangent, secant, antiderivative of cosecant, cotangent will be a negative cosecant, and the antiderivative of cosecant squared is a negative cotangent, the integral of sine is a negative cosine. So all these integral rules, you're just starting on the right side of your derivative rules and moving left. If you can find an empty space or because I'm going to save worksheet 3 for us to do tomorrow in our morning help session, but you can also try those problems on your own tonight as you review for your quiz. Okay, so I want to do a problem that that is not on your quiz review. So if you can find either in your notebook or I want to do a power rule problem here. Okay, go ahead and write this problem down. Five x squared minus 7x cubed plus 3, all divided by 2 root x. Again, there's no quotient rule for antiderivatives. We have to rely on power rule. But before we can apply power rule, what would your first step be? Yeah, okay. Root x, that's x to the 1/2. But what should we do after that? Say it again. So you could bring it up to the top and then distribute through. I prefer this way. I prefer to split up into individual fractions. And then once everything is separated, then move it up to the top. Now, having said that, there are different ways to do this. I like to present it this way. I feel like there's less potential mistakes this way. But if you want to bring that x up to the top as x to the negative 1/2 and then distribute through, that's fine as well. But I'm going to present it this way. I think this is a little bit more clear. Okay, we're still not ready for power rule, but at least we've individualized each problem. Okay, so now I have 3 distinct problems that are independent of each other, and we just have to clean up every one of them. Right at the beginning, this is all connected in ways that makes it difficult to resolve, but at least this next step, we're beginning to separate these problems away from each other. But the x's are still out of place. So how do we resolve the x's? So we're still not ready for power rule. What would you do? Because this x is out of place, right? How do we merge them together? Yeah, subtract the exponents. You could bring this x as x to the negative 1/2 and then add the exponents, or you can just leave it in this form and subtract the exponents. Okay. So what's 2 minus 1/2? But 4/2 minus 1/2 is 3/2. And as I do that, you're still holding on to the integral notation. And then I'm going to pull all these denominators out as a fractional value so that it doesn't, it feels a little bit cleaner, not having to stare at a number below my variable. Okay. 3 minus 1/2 is 6/2 minus 1/2, which is 5/2. And then this can come up, right? This is just x to the negative 1/2. Everybody okay so far? I see some students leaving this as their answer, but this is only getting you to the beginning right before power rule gets applied. So we're not done yet. Okay, we still need to do our calculus step. So all these are equivalent to each other. We've just turned it into something that power rule can have an easier time managing at this point. Now we can do power rule. Okay. So the 5/2 is just a coefficient, doesn't go anywhere. We just have to worry about adding 1 to our current exponent. So if I add 1 to 3/2, I get 5/2. Add 1 to 5/2, I get 7/2. And by the way, it's just a coincidence that these numbers are matching with the exponents here. That I didn't mean for that to. No, we can't expect that to happen. 3/2 stays. Add 1 to this exponent. Now that we've done power rule, our integral and our dx notation can drop out. In place of it, we'll do a plus c. And then I'm going to try to resolve these complex fractions here. So dividing by 5/2, the same thing as multiplying by 2/5. Dividing by 7/2, the same thing as multiplying by 2/7. Dividing by 1/2, the same thing as multiplying by 2. Fives cancel out, twos cancel out. Sevens cancel out, twos cancel out. Okay, it's not always going to happen like this. I think it's just. Yeah, so don't expect, all these fractions to always cancel out. Whatever leftover coefficient in front, you just have to keep it. Okay, you'll see a problem like this on your quiz. Any questions about these steps? Okay, so we've pretty much gone through 2 sets of worksheets. That is basically what your quiz is going to look like, front and back page. Plus, I'll give you a formula sheet with the summation formulas and the area definition rule. Make sure you memorize your your trapezoid rule, your area of a rectangle, power rule, and then break intervals. Guys, one thing I want to point out is, first off, tomorrow, help session, 7:15. I'll send out a reminder this afternoon. You'll get to use your calculator. Homework. I forgot to put the pages, the textbook pages in your packet, so I'll print those out separately and I'll give it to you tomorrow. Obviously, your homework for this new section is not due until next week. Now, next week, Monday, we have no school, right? MLK. I don't know what the weather is going to hold next week. I don't know what the situation is, but if we're for some reason not going to have school for certain days, I still want to have daily lessons on Teams. So I'll still do what I did on Friday, previous Friday, where I invite you guys to join for a lesson, and then if you can't make it, just be sure to watch those videos. I mean, if we're missing multiple days next week, I'll probably shorten the homework, but just ask that you guys watch the videos and just keep up with the lesson. Okay. I can get your phones. Oh, my God.